As I was reading this problem, I realized that the way it was written, there were was only one significant figure on each of the two numbers that I gave here. And I just don't find problems with one significant figure all that interesting. So I think I'd like to rewrite this one and say that it has a speed of 50.0 kilometers per hour and the angle is 60.0 degrees. Now, we have a car traveling due east with a speed of 50 kilometers per hour. This would be the speed or the velocity of the car with respect to the Earth. Rain is falling vertically with respect to the Earth. So we know the velocity of the rain with respect to the Earth. The traces of the rain on the sides of the window of the car make an angle of 60 degrees with the vertical. Find the velocity of the rain with respect to the car. So the first thing they told us was the velocity of the car with respect to the Earth. Now, it says it's due east. So I think I'm going to set up a coordinate system where east is the x direction, the I hat direction, and north is the y direction, the j hat direction. So the velocity of the car with respect to the Earth, it's going due east. That means it is 50.0 kilometers per hour in the I hat direction. So that one's nailed down. Then it says rain is falling vertically with respect to the Earth. That means that the velocity of the rain with respect to the Earth, it's coming straight down. Well, we don't actually know its speed, but I can just write it as VR/E, the magnitude of it, and it's in the minus j hat direction. So I'll put a minus sign in front of it and call it j hat. Actually, this isn't north, this is up. So east is in the I hat direction. And then the traces of the rain on the side windows of the car make an angle of 60 degrees with the vertical. We don't know what the magnitude of that speed is, but this would be the rain with respect to the car. And just to give you an idea of where we'll be going, the velocity of the rain with respect to the Earth will equal the velocity of the car with respect to the Earth plus the velocity of the rain with respect to the car. So we'll be adding some things together here. Unit-wise, I'm going to stay with kilometers per hour. There's no reason not to. We don't know the magnitude of the velocity of the rain with respect to the car, although that will soon become somewhat apparent. But if I make a little sketch of it, if the car's going that way and the rain's actually falling straight down, I would expect a side view to show something like this. It makes an angle of 60 degrees with the vertical, so maybe that's about 60 degrees. And this will be 60.0 degrees. This will be the magnitude of this will be the velocity of the rain with respect to the car. This over that will be the cosine of 60 degrees. So this will equal VR/C cosine of 60 degrees. And this will be, this over that would be the sine of 60 degrees. So this will be VR/C sine of 60.0 degrees. Now this is going to be away from the eastern direction, and this is going to be down. This is in the minus j hat direction. So if I write this, it'll be minus VR/C sine of 60 degrees in the I hat direction, and minus VR/C cosine of 60.0 degrees in the j-hat direction. And that was all just using information that they gave me. I was able to figure out those things. Now it turns out some of these are equal to each other, some of these things, but let's go ahead and write it down. The relative velocity equation would be the velocity of the rain with respect to the earth will equal the velocity of the car with respect to the earth plus the velocity of the rain with respect to the car. Well, what can we get out of this? Let's go ahead and write these down in component form. We would have on the left side of the equation, that's the velocity of the rain with respect to the earth, just this. So minus the velocity of the rain with respect to the earth in the j-hat direction will equal, whoops, this is supposed to be the velocity of the car with respect to the earth. Velocity of the car with respect to the earth is 50.0 kilometers per hour in the i-hat direction. The velocity of the rain with respect to the car is what comes next. So I'd have minus the velocity of the rain with respect to the car times the sine, didn't close that parenthesis, of 60.0 degrees. And that's in the i-hat direction. And then I have minus the velocity of the rain with respect to the car times the cosine of 60.0 degrees in the j-hat direction. Okay, well, we've got a vector expression here. The j-hat terms from one side will equal the j-hat terms from the other. The i-hat terms from one side will equal the i-hat terms from the other. Let's do the i-hat terms first. There's no i-hat term here, so on the left side we'll have 0 is equal to the sum of these two things. And now we're in scalars. We're just lumping together the i-hat terms. So I'll have 50.0 kilometers per hour minus the velocity of the rain with respect to the car times the sine of 60.0 degrees. And that equals 0. Well, I can do a little bit of work here, and I would find that if I kick this term across and then divide both sides by this, that's two algebra steps at once. I'd get the velocity of the rain with respect to the car is going to equal 50.0 kilometers per hour divided by the sine of 60.0 degrees. That's something I can just do in a calculator. I get 57.7 kilometers per hour for this. So now I know the magnitude of the velocity of the rain with respect to the car. I can just take this value and plug it into one of the other equations there to figure out that other one. If I do the j-hat term, I would get minus the velocity of the rain with respect to the earth. Whoops, that's supposed to be a v, is going to equal minus the velocity of the rain with respect to the car times the cosine of 60.0 degrees. The velocity of the rain with respect to the earth is equal to, I can take this value, drop it in there since I figured out its magnitude. I get that the velocity of the rain with respect to the earth in magnitude is 28.9 meters per second. And I think I know everything I need to know. It says find the velocity of the rain with respect to the car. Well, rain with respect to the car, I actually may have figured this out. Well, I figured out I'll have to multiply this number by those things. So velocity of rain with respect to the car is going to equal the negative of the magnitude of that, 57.7 kilometers per hour, times the sine of 60.0 degrees minus that magnitude again, 57.7 kilometers per hour. Oops, that's in the I hat direction. And this will be cosine of 60.0 degrees in the j hat direction. So got a little bit crowded. So that's what the velocity of the ring with respect to the car comes out to be. It's not surprising here, we actually could have figured this out intuitively, that the velocity of the rain with respect to the car in the I hat direction would be just the speed of the car, but in the opposite direction, because that horizontal motion that you experience in the car is entirely due to the speed of the car because the rain is falling straight down. And then the velocity of the rain with respect to the earth has only a vertical component, and it's just going to be minus 28.9 meters per second in the j hat direction, straight down. So there we solved our second to last problem. Let's take a look at the last problem here. This was one that I actually used on a test a few years ago, and so solving this one you'll find out what my test questions look like. A canoe has a velocity of 0.400 meters per second southeast relative to the earth. Oh, okay, so already we know the velocity of the canoe relative to the earth is going to be 0.400 meters per second at, now that's just a speed, but when I tag this on, the direction on, turns it into a velocity. Not our usual way of writing it, but that's okay. And I'm going to write it as south of east. Then over here, I'm going to make myself a little coordinate system. This way is east, this would be north, this will be south, and I'm going to let this be my I hat direction, and this direction would be my j hat direction. Anything that's pointing south is going to be in the minus j hat direction. So there'll be a component of this that's in that direction. And I'll just make a quick little sketch here for figuring this out. I've got a vector, 45-degree angle, more or less, and this is 0.400 meters per second. This component here will be 0.400 meters times the cosine of 45. This will be 0.400 meters per second times the sine of 45. Similar to the initial velocity in projectile motion, since the sine and cosine of 45 are the same thing, I'd expect both of them to be the same, and it actually comes out 0.283 meters per second there, and 0.283 meters per second there. So the velocity of the canoe with respect to the earth, despite how sloppy I wrote that, is going to be 0.283 meters per second I hat in the east direction minus 0.283 meters per second in the j hat direction. What else are we given? The canoe is on a river that is flowing 0.500 meters per second east relative to the earth. Oh, okay. So that's the velocity of the water with respect to the earth, the water in the river. Okay, and they give me the magnitude of it, 0.500 meters per second, and they tell me that it's flowing due east, which in my coordinate system, that's the I hat direction. I can say that. What do we usually have in these problems? I now know two of the vectors involved, The other one would be the velocity of the canoe relative to the river. I'm going to write the vector equation here, that the velocity of the canoe relative to the earth is equal to the velocity of the water relative to the earth plus the velocity of the canoe relative to the water. I know this, and it's this that I want to know. So the velocity of the canoe relative to the water, I'll be able to figure it out in I hat, j hat components easily, although they want it in magnitude and direction, but I can figure that out once I know the components. So it'll equal the velocity of the canoe relative to the earth, which they told me, minus the velocity of the water relative to the earth. So velocity of the canoe relative to the earth is this thing. So 0.283 meters per second in the I hat direction minus 0.283 meters per second in the j hat direction, minus the velocity of the water with respect to the earth, minus 0.500 meters per second in the I hat direction. So this is just a little bit of arithmetic to figure out that velocity of the canoe with respect to the earth. And 0.283 minus 0.500 ends up giving me minus 0.217 meters per second in the I hat direction, minus 0.283 meters per second in the j hat direction. So there's the velocity of the canoe relative to, should be a W here. Yep. Hope you weren't too confused by that. That's the canoe relative to the water. I'm going to make a quick sketch of that just to show myself what's going on. Both I hat and j hat are negative, and I'll have 0.217 meters per second in that direction. I'll have 0.283 meters per second in that direction, and I'm going to measure the angle. West is that way. I'll be measuring an angle south of west, just call that phi, and phi will be the inverse tangent of 0.283 divided by 0.217. When you take this ratio, the meters per second will divide out, although I'll go ahead and write them down. Phi happens to equal 52.5 degrees. It's an angle. Figuring out the magnitude of this, I'd have the velocity of the canoe relative to the water is going to be the square root of 0.283 meters per second squared plus 0.217 meters per second squared. And when you're doing the Pythagorean theorem, it doesn't matter if the components are positive or negative or anything. You're just after the magnitude of a vector, and you can ignore those minus signs. When you wrap this in parentheses, they'll square away, so don't worry about those. Velocity of the canoe with respect to the water, or the speed of the canoe with respect to the water, ends up being 0.357 meters per second, and the angle is pointing 52.5 degrees south of west. And when we say it that way, we mean you go in the westerly direction and rotate toward the south by 52.5 degrees. Okay, that's our last example problem, studying motion. The next thing we'll do is start understanding what causes motion. That will involve Newton's laws.